Okay, and now it gives me great pleasure to introduce and to have Professor Serban Stratila from, I said INCREST, and I should correct it by him.
I will correct
He
it.
will correct me. So I will. I've said enough nonsense already. So I'll let Serban take.
Thank you. So first of all, I would like to thank the organizers for giving me this nice opportunity to speak to you and to be in a very nice country, India. Concerning my affiliation, since 50 years, I am in the Institute of Mathematics of the Romanian Academy. That means if you like abbreviations, this is Institute of Mathematics of Academy Romanian. And that's INCREST didn't exist, actually. Even when you came to Romania, INCREST didn't exist more. It was just a fake institution, and the other affiliation is at the University of Bucharest. So I will begin this first lecture with some motivation for the theory we will see developing. And I will begin, so by some notation, M in B of H will be always a von Neumann algebra. And on a von Neumann algebra, you have several topologies. Weak operator topology, strong operator topology, and a topology which I denote by W and call the natural topology on the von Neumann algebra is what Dixmier calls the ultra-weak topology. Roughly, this topology is obtained by looking at all functionals which are WO continuous on B of H and taking the closure. So you take B of H, say tilde, this is the dual of B of H in the topology WO. Then you take the closure of this in all the dual, and this will be B of H star. Well, the W topology is the weak topology on B of H given by B of H sub star. What is important, and the fact that I call this topology the natural topology, is the fact that this topology is transported by star isomorphism. Any star isomorphism is W continuous. That's all. Besides motivation for the theory that will come, I say that this theory, the Tomita-Takesaki theory, addresses mainly to the spatial theory of von Neumann algebras. And so I will begin with a few things connected with the spatial theory. By the way, in the afternoon, I propose to you, I present to you the von Neumann spatial theorem and its consequences.
Excuse me, Serban. What is the tilde again?
Sorry?
B of H tilde.
B of H tilde, B of H tilde are the functionals phi B of H in C, that phi is VO continuous. And the topology W, the ultra-weak topology of as named by Dixmier, is okay. So that I repeat, in the afternoon I propose to you 1 hour I present the main result of von Neumann concerning the spatial theory. I will use it here. Now, let's take psi a vector in H. And then you can form the subspaces M psi and M prime psi. and take the norm closures in H. This space is invariant to M. Consequently, the projection onto this space, which I will denote by P prime psi, will belong to the commutant of M. And this one, I will denote it by P sub psi without a prime, and this will belong to M. Well, these two are the cyclic projections in M prime or in M associated to a vector psi. And it is an easy thing to see that the central support of P psi is equal to the central support of P prime psi. It is the projection onto M prime psi. The central support of a projection means the least central projection that multiplying this leave it on the place. Okay. Now, if you have P psi, P prime psi, it's equal to 1, this means that M psi is dense in H. And that, in that case, we will say that psi is a cyclic vector. For M, of course. If P psi is equal to 1, then M prime psi is equal to H. And of course, psi is cyclic for M prime, but this is exactly the same thing as the following implication. If X is in M, and X psi is equal to 0, then X is equal to 0. You can see immediately at least one. If X psi is 0, then X prime psi is X prime X psi is equal to 0. So that X on X prime psi is equal to 0, so that X restricted to this subspace is equal to 0, so that restricted to the whole space is equal to 0, sorry. So that in this case, psi will be called separating for M. Okay, and so that a vector is separating for M means this thing, if and only if it is cyclic for the commutant. Okay, now the existence of cyclic or separating vectors is not a very seldom fact. Namely, if M in B of H is of countable type, that means that every family of non-zero projections which are orthogonal is at most countable. If B of M in B of H is of countable type, then there is a central projection in Z of M such that MP included in B of PH has a cyclic vector and M1 minus P included in B1 minus PH has a separating vector. This statement becomes very clear if I assume that M is a factor. So a factor which is countably decomposable of countable type has either a cyclic vector or a separating vector. And that's easy to see because you take psi n. Now, the countability is ensured by the assumption here. Psi n are vector in H, such that P sub psi n are mutually orthogonal, and P prime sub psi n are also mutually orthogonal. Then I assume, moreover, that psi n, say, it has a norm 1 over 2 to power n. Is the same thing. And then I can consider the vector psi, which is the sum of the vectors psi n. Because the projections P prime psi n are orthogonal, we have that P psi is equal to the sum of P psi n. Sum over n. This is not automatically from here to here. It's not true. But it is true if, say, the brothers of the P psi n are mutually orthogonal. And for the same reason, P prime psi is equal to the sum over n P prime psi n. Okay. I take the family psi n maximal with these properties. This means that 1 minus P psi times 1 minus P prime psi is equal to 0. And this implies, I will say first in the case of factors. In the case of factors, this implies that either this element is 0 or this element is 0. In general, if you have two elements in a factor, x prime is equal to 0, this happens if m is a factor, if and only if x is 0 or x prime is equal to 0. So you see, in the case of a factor, you have either a separating vector or a cyclic vector. If you are in a von Neumann algebra, then take, I don't know, P I'm looking for there is 1 minus, I don't know exactly if is this 1 minus P prime of C. Sorry, 1 minus the central support of 1 minus P prime of C. And if you take this, you get immediately the result. What I don't know, and I don't stay now to check, if I have here P prime or I have P. Because, you see, this has a cyclic vector, this has a separating vector. So you should manage with them. Okay?
So this is the definition of countable type, or what?
No, the definition of a countable type is that any family of non-zero orthogonal projections is at most countable. And because I assumed M of countable type, here I could put a sequence, and consequently I could make this assumption. Because otherwise, if it is an infinite family, I have not 1 over 2 to power I, an infinite index or so. So that the appearance of a cyclic or a separating vector is not very seldom. Okay, now, if M is abelian, that means M is contained in the commutant, then any vector which is cyclic for M is cyclic also for M prime. That means every cyclic vector is also separating. So that in the case M is abelian, there is, and in the countable, the composable, there exists always psi, a separating vector. If M is maximal abelian, that means M is equal to M prime, then there is a cyclic vector. So that in the countably decomposable case, we see that the existence of cyclic vectors is not a very particular situation. Of course, you don't know, is it separating or cyclic? Now, if a vector, just a moment, if a vector is both separating and cyclic, I will say that it is bicyclic. Bicyclic means cyclic and separating. Please, sir.
Yeah, the existence of the vector psi n, is that obvious? Is that obvious to construct psi n such that p psi n's are orthogonal and p prime psi n's are also orthogonal? Is it?
Well, you take a maximal family with these ones mutually orthogonal among them and this one mutually orthogonal among them. You can have just one. I mean, p psi. If you take a vector psi 1, then p psi 1 and p prime psi 1 will do. But maybe there are many. And then I took a maximal family.
You don't demand that they add up to 1.
Sorry?
You don't demand that the projections p psi n add up to 1.
No, I don't ask this is equal to 1. But if you are in a factor, either this is equal to 1 or this is equal to 1. And that's okay. Okay. Now, I will show that if a von Neumann algebra has on one side a cyclic vector and on the other side a separating vector, then it has a bicyclic vector. So that proposition, you have M in B of H of von Neumann algebra. Suppose that there is a vector psi which is cyclic, P prime psi is equal to 1, and a vector eta such that P eta is equal to 1. Then there is a vector zeta H such that P zeta is equal to P prime zeta is equal to 1. So that if a von Neumann algebra has a cyclic vector and has also a separating vector, then it has a vector which is simultaneously cyclic and separating. Now, the easiest argument for this is the fact that Dixmier and Maréchal proved that the set of cyclic vectors is either empty or a dense G delta in the Hilbert space, which is a rather elementary proof. And then the set of cyclic vectors is a dense G delta, the set of separating vectors is a dense G delta, or the intersection by the Baire theorem, for instance, the intersection of 2G delta dense is non-void. So that this proves this thing. But on the other hand, I would like to show to you an alternative proof using the spatial theorem of von Neumann, namely the following thing. By the way, I can quote Ognanu for this proof. Look, so by assumption, I have P eta is equal to 1 and P prime C is equal to 1. So that I have this situation, P psi is less than the identity, which is P eta. Now, this implies by one of the forms of the von Neumann spatial theorem that also P prime psi is dominated by P prime eta. Now, this is less than 1, but this is equal to 1. That means that P prime eta is equal to 1. Okay. You know it's equal, it's equivalent to 1. So that this means the following thing. 1 is V star V for a partial isometry in M. and V star is equal P prime eta. And the partial isometry V belongs to M prime. And then we have the following situation. We have P prime V star eta. It's equal to, I always write that a projection is equal to the space on which it projects. So that this is M V star eta. This is equal to V star M eta, because V is in the commutant. This is V star M eta, because V star is a partial isometry, and this is equal to 1. Because this thing here, V star V, is equal to 1. So that on the one hand we have this, on the other hand P V star eta, it's equal M prime V star eta. It's equal, is greater than M prime V star eta, because here are less elements than in the whole M prime. Okay, this is equal to M prime P prime eta eta. V star is P prime eta. This is eta is in the space of projections P prime eta, so that this is M prime eta. It's equal to P eta. And this is bigger than M prime V star eta. Why? Because P eta is M prime eta, and here is M prime times an element in V prime, V. So that there are less elements in here than in the whole M prime. And this is P V star eta. So that I have the following thing. P eta is also equal to 1. Not only P prime eta, this implies that P eta is equal to 1. Because P V star eta was yeah, it was somewhere. This was equal to 1, but I don't know where. I'm sorry?
P eta equals 1 is the assumption to start.
Yeah, P eta is the assumption. No, then what I have, well, okay, that's perfect. P V star eta, it's equal to P eta, which is equal to 1. This is an assumption, as you said. Thank you. So that this one is equal to 1. On the other hand, we saw that also this one is equal to 1. So both of them are equal to 1. Hence, the vector V star eta is a bicyclic vector. And that's the end of the story. Now, the discussion will be centered around the following notion, the notion of a standard von Neumann algebra. A von Neumann algebra M in B of H is called in standard form if there exists a conjugation J defined on H with value in H. Now, what is a conjugation? It is a self-adjoint unitary operator, but not linear, but conjugate linear. So that this is G star is equal G minus 1 is equal G. This means, but the operator J is not linear, it's conjugate linear. There is a conjugation such that the following map, let's call it little j, from M, taking an x from M, going to Jx star J, goes to M prime and is a star anti-automorphism acting identically on the center. That means J Z star J is equal to Z for any Z in the center of M. Now, first remark is the following. Suppose M in B of H is in standard form. And countably decomposable and of countable type. Okay. Then there is psi naught, a bicyclic vector for M. Well, let me do it simpler. Because of the fact that J is acting identically on the center, that means for a central projection I have G, P, G is equal to P. I may assume that there is either a separating vector or a countable vector. If not, I go on the two central projections there. So that suppose psi 0 is, for instance, M psi 0 is equal to 1. This means that P prime psi 0 is equal to 1. Okay, then let me see. I have that J M psi 0 J M psi 0 is equal to the whole H. Then this means also that J M J psi 0 is equal, this is equal to M prime psi 0. So that if I have a vector which is cyclic for M, I will get a vector which is separating for M. That means cyclic for M prime. Having a vector which is simultaneously cyclic and separating, by the previous remark, it follows that there is a bicyclic vector. Now, the Tomita-Takesaki theorem says that essentially the converse of this affirmation. If you have a von Neumann algebra having a bicyclic vector, then it is in some standard form. What it remains to make point precisely what is J, but this is mainly the statement of the Tomita-Takesaki theorem. Now I will go further, and I will consider two special cases. To see in what consists or should consist the proof of the general case. I repeat, the general case of the Tomita-Takesaki theorem is the fact that if you have a von Neumann algebra with a bicyclic vector, then it is in standard form. The first proposition and the first result on the type of the theorem we are interested in appeared in single operator theory. It was about normal operators. Normal operators having a cyclic vector had simple multiplicity, whatever this means. It will mean what I will say immediately. But this was obtained first in single operator theory. The proposition I have to show is you have M in B of H, a von Neumann algebra which is commutative, and you have Xi in H, a cyclic vector. To be precise, this means M Xi it's equal to H. Then M is maximal commutative. M is equal to M prime. And that means actually also the simple multiplicity for a normal operator. Okay. Proof. So let X prime an element in M prime. We have that M Xi is dense in H, so that there is a sequence of element AN. By the way, you see the notation I use, and I will always use. The elements in M will be small letters like AN, and the elements in AM prime will get a prime. Just in order to see very easily what commutes with what. So there is a sequence of elements in M such that AN Xi, let me put here Xi 0. AN Xi 0 converges to X prime Xi 0. Well, the main thing that happens in this proof is the fact that this will imply the fact that also no, let's yeah, that also AN star Xi naught converges to X prime star Xi naught. And we will afterwards recognize in this thing the germ of the theory we will develop. Well, to show this thing, we observe first that the norm of AN star Xi naught, its square is equal to AN Xi naught. You will say because of the commutativity, because if you put here the square, here you have AN star Xi naught psi naught, while here you have an star, an psi naught, psi naught. So you will say first because of the commutativity, but keep in mind that this happens because a condition which is weaker than the commutativity. We will see immediately this thing. On the other hand, now, what I will show that this happens weakly. Because they are bounded, I have to check this convergence in scalar products with elements in a dense set, so that I consider an star psi naught, b psi naught. And if I show that this converges to x prime psi naught, because this is a dense set in the Hilbert space, and the fellows here are bounded, it means that it happens that this converges weakly to x prime. Well, this is almost immediate. Namely, this means b, well, it's b star an psi naught, psi naught. This is equal to an b star psi naught, psi naught. Again, because the commutativity, but a weak form of the commutativity. Sorry?
That should be an star, no? This is the second term.
Where?
The second term. B star, an star, right?
An star times some b star. Some b. Just any b
The next term.
here.
That should be an star.
I'm sorry, I missed to put a star there. It's okay, thank you. It's an star. This commutes again is b star an star psi naught, which is equal to an star psi naught b psi naught. Well, I'm going back with this way. It's equal to b star psi naught times an psi naught. This converges to b star psi naught times an psi naught converges to x prime psi naught. And now I do the same thing. I put b in the other side, and I come with x prime here, so that this will be x prime star psi naught times b psi naught. So that this being arbitrary, it follows that indeed an star psi naught converges vaguely to x prime psi naught. I would say this is the main part of the proof, and it was just a line. Okay, now I take another element, y prime, belonging to m prime, and I want to show that x prime y prime is equal to y prime x prime. That means that the commutant is commutative, and this means that m is equal to m prime. Okay, so x prime, y prime, b psi naught, c psi naught. Okay, this is equal to y prime b psi naught, x prime star comes here and jumps over c, because this is from the commutant. So that this is c x prime star psi naught. Okay, now this is equal to the limit with over n of y prime b psi naught c and x prime star psi naught is the weak limit of an star psi naught. Okay. This is equal to the limit in n of y prime b psi naught times an star c psi naught. So here we used in full the commutativity of the algebra, not just something like a trace property like here. Now I will go with this an here, and this will give the limit, because an comes here. It commutes with y prime. It commutes with b because the algebra is commutative. It joins psi naught, and an psi naught converges to x prime psi naught, so that this will be the limit, is gone the limit, y prime b, and here will be first, before the limit, an psi naught, and an psi naught converges with to x prime psi naught, c psi naught. Now x prime and b do commute. So I have here x prime b. And now look, y prime x prime is equal to x prime y prime. So this completes the proof. And let me repeat that the main thing here was this implication. And this implication didn't require too much the commutativity of the algebra. So that let's consider a little more general result. This one was stated by von Neumann, Murray and von Neumann, or von Neumann, I don't know. Namely, the following statement. Proposition again. I have M in B of H. Psi naught in H, a cyclic trace vector. Let me write what means. Means M psi naught is equal to H, and AB psi naught is equal to BA psi naught. Okay. Then psi naught is also separating. So it is a bicyclic, cyclic vector. Is also separating. Okay, and there is a unique conjugation. J such that J of A psi naught is equal A star psi naught, and then this for every A in M, and then the map J defined on M, taking an X into J, X star J, belongs to M prime, is a star anti-isomorphism acting identically on the center. That means, but in a more precise form, that the algebra M is in standard form. Okay, now, proof. Let's take x in M such that x psi naught is equal to 0. I want to show that x is equal to 0. Then I have the following thing. X A psi naught, psi B psi naught. That happens for every A and B in M. This is equal to B star x A psi naught psi naught. All the elements in here are elements in M, so that I can commute them because of the trace property. These two, this is A B star x psi naught, which is 0, because this is 0. So that the vector is also a separating vector. And now we go, yeah. I look at the map from M psi 0 containing an A psi 0 going to A star psi 0, which belongs to M psi 0 again. Because of the trace property, this map is an isometric map. So that this map will give rise to a conjugation. You see, A star xi naught goes into A star xi naught, so it is conjugate linear. This is a conjugation which is uniquely determined by this. J of A psi naught is equal A star psi naught. Well,
Serban,
yeah,
I'm sorry, I got lost there.
Where?
How did you get the last step?
here
Yeah.
I assume that x psi naught is 0. Because I could commute here B star x with A, x approaches to psi naught, so it is 0.
Why can B star x compute with A?
Again, I assume that x psi naught is equal to 0. In order to show that psi naught is separating, okay, is that okay? Right? Fine. So I saw that this is 0 for every A and for every B, so that this is perpendicular on the whole space because these are dense in H. So this is 0. Now x is 0 on what? On the set. So x is equal to 0. So that now this map is an isometry. Let me check again. A star psi naught square is equal to A star psi naught, A star psi naught. It's equal to A star psi naught, it's equal to A star A psi naught, because of the trace property of the vector psi naught. And this is equal to A psi naught square. So that this map is a conjugation which is uniquely determined by the fact that J of A psi 0 is equal to A star psi 0 for A in M. Okay, now it is very easy to show that this map takes values in M prime. And namely, I make J x star J y, where x and y are in M. And I take also an arbitrary A in M. And I put here A psi. This is equal to J X star, this means A star, Y star, psi naught all over. And this is equal Y A X psi naught, because J acts exactly by the thing I saw there. And this means this is equal to Y J of X star A star psi naught, which is further equal to Y J X star J X star J A psi naught. X star is X star from here. J A psi naught is A star psi naught. And this is further equal to what I want. It's nothing. You see, this thing is in this order, and here this thing is in the other order, so that J X star J commutes with any Y. So that what we should show is that this map is surjective, or that the analogous map for M prime going to M has the same property of going to M. Now, the problem is the following. If we had the formula J X prime psi naught is equal to X prime star psi naught for X prime belonging to M prime, if we had this thing, then exactly the same proof as there would show that J M prime J goes to M second. That means to M because of the von Neumann bicommutant. So again, the main point here is to show that defined in this manner on M psi naught, it has the same behavior on M prime psi naught. And this is done okay. So I want to show that J A prime, in order to have the same notation as in my cheat sheet. Okay, so I have to show this thing. Well, I take AN in M such that AN psi converges to A prime psi. Then we have that AN star psi, this is J of AN psi, this AN are in M, so that AN star is J of AN of psi naught. Okay, and this converges to J of A prime psi naught. Okay, on one side. Now, if I take any B in M, I will see the following, that I have a weakly convergence, namely AN star, a weak convergence, psi times B psi is equal psi AN B psi. It's equal, because psi naught is a trace vector, I can reverse this in here. So that this is psi naught A B A N psi naught. Now, this converges to what? To psi naught. Here is B, and here is A prime psi naught. A prime will commute with B and will go back in here. So this is equal to A prime star psi naught B psi naught. So we see again, because big psi naught is here and is also here, because this sequence is, again, it's isometric. An star psi 0 is equal to, in norm, with An, with norm of An. It's equal norm of An psi naught. So, because this is convergent, it is bounded, so this sequence is bounded, and this convergence takes place for any vector in a dense set. That means that An star converges weakly, An star, sorry, psi naught, converges weakly to A prime star psi naught. Now, we have here a convergence to this, and we have here a convergence to this. So the two guys are equal. So that now I know that J acts in the same manner by the star operation also on M prime. So that I get exactly with the same proof as above that J M prime J is included in M second. That means in M. And this proves the theorem. Now, this theorem was known since von Neumann. Of course, it is an extension of the previous theorem concerning abelian and maximal abelian, because I didn't check, but this is an easy exercise, that it acts identically on the center. It is a very easy exercise, this. Now, if M is commutative, the center is the whole thing. So that this map is surjective here, which is just M included in M prime. That means M is equal to M prime. So that this is a particular case. Now, what one would know is how to extend this theorem to a more general case. If we compare the first proposition with this one, we say, well, we could put aside the fact that the algebra is commutative for most of the proof. Well, but then what is the conclusion? Because there it was maximal commutative. Well, the conclusion was now expressed in terms of J. That means that, well, this map is a star anti-isomorphism acting identically on the center. Now, the problem further is, let's take just a B-cyclic vector. Then the problem is, what is J? How to find a J? And now Masamichi can say to me, if this was the original idea of Tomita, was I have to look for the star operation and find the J inside. Okay, now what will happen? We will see that in general, at the level of the Hilbert space, the star operation is a closable operation. Being a closable operation, it has a polar decomposition. Now, the polar part in this decomposition will be a conjugation. And it remains to prove Jmj is equal to M prime. This reminds me Alain Cohn in Paris, working with your book and making like so on it. So everything, the statement is clear. What is the proof? Something like this. Okay, good. Let's go a little bit further now. And further is the following thing. If the algebra is not countably decomposable, then it never has a separating vector. So it never has a bicyclic vector. So what to do in this case? The first problem that arises is, are we really interested in this? Well, we are interested first because if the algebra is not countably decomposable, then there exists no fightful normal state. And then there should be some other thing. Well, there are weights. I will give the definition immediately. But why to look to the weights? We can say, well, we do everything in the countably decomposable situation, and then we can extend the results. This is indeed possible. And the fact that we consider not countably decomposable algebras, we say, well, they are rather peculiar. Not this is the reason to look at the weights. The reason to look at the weights and to look at the situation where there are no bicyclic vectors appears later. We will see a celebrated theorem of Alain-Kohn, which once a weight is fixed, the other weights are given by cocycles. And to the cocycles correspond all weights, not only normal functionals. Okay, so let's go to the formal definitions. So that you have phi on M, the positive part of M, with values in 0, infinity allowed to. This map is conditionally linear. That means if x and y are in M plus, then phi of x plus y is equal phi of x plus phi of y. And if you have a positive lambda, even with 0, we have phi of lambda x is equal to lambda phi of x. 0 times infinity is equal to 0. So this means a weight. And as much as I know, the weights were introduced early before the Tomita-Takesaki theory by Francois Combes. Good. Now, properties of a weight. We'll say that the weight phi is fightful, means that if A is positive and phi of A is equal to 0, then A is equal to 0. Okay. We will say that phi is normal Well, we have to be very careful here. We say that phi is normal if phi is the supremum of f for f in f, where f is a family of normal states, normal positive forms, increasingly directed. Well, this implies, obviously, the fact that phi is W lower semicontinuous. Every supremum of continuous functions is lower semicontinuous. And this implies the following thing, that phi of sup of AI, I in I, it's equal to sup of phi of AI I implies in I, when the AI in M plus is an increasing net. All these implications are obvious. The fact is that there is a very difficult implication, namely, this condition ensures that phi is the supremum of a directed family of positive normal linear functionals. A little bit, this is due to Hagerup. And the proof is quite a proof. It's a technically difficult proof. So that afterwards, Pedersen and Takesaki showed that these conditions are also equal to the fact that phi is the sum of a family of functionals. If I remember well, this was done using the Pedersen-Takesaki construction and the construction given by Kohn in some other context. We will arrive there and we will point out. For us, the definition of normality will be this one. Now, for a phase in general, we denote by f phi r the I in A in M plus, such that phi of A is less than infinity. This is a phase. That means it is a convex cone which is hereditary. An element which is less than an element in the phase is still in the phase. Then n phi is equal x in M, such that phi of x star x is less than infinity. That means it is in the phase. M sub phi will be n sub phi star n sub phi. That means sums of elements of the form B star A. Okay, there is one thing, namely that M phi is equal to the linear span of the phase F phi, and that the positive part of M phi is exactly F phi. This means that we can extend phi to a linear functional on M phi with values in C, which on the F phi coincides with the one which is given in here. Now, the third notion we will need is what means that phi is semi-finite. The fact that phi is semi-finite will mean the fact that M phi is weakly dense, that topology, the natural topology, in M. Well, this appears to be the same thing as n phi closure V is equal to M. And what is important is that if phi is semi-finite, then there exists net AI in F phi such that AI tends increasingly to 1. And we will use this thing, which is a consequence of the definition. Well, there is something to work, but okay, so that we may consider weights. Weights, this exists. On a countably decomposable algebra, there are normal states. On an algebra, any algebra, there are normal, semi-finite, and fightful states. This will be an abbreviation, NSF. Why? Because you simply take a maximal family of normal states, a maximal family of normal states with orthogonal supports, and you add them. And you get then exactly a weight which is normal, semi-finite, faithful. Now, if you have a normal state, you have the GNS construction. The GNS construction for F, a normal state, gives you a representation PF of M onto B of H, F, and a vector psi F, which is cyclic, PF of M psi F is equal HF, and which gives back the state, namely F of X is equal, let me put it so, PF of X psi F psi F. And I like to put it also in this manner, psi F omega psi F times P phi of X, where in general omega psi F, excuse me please, psi F. In general, by omega psi, I denote the vector state. Operator T goes to T psi, scalar product with psi. Of course, we should point out what is also the context. I mean, it is a state on the whole B of H, or only of a subalgebra, and so on. So that this looks very nice, and it is the famous GNS construction. So what happens now is, what happens if I have an NSF weight? What do I have? I will no more have the vector. This thing is killed, doesn't exist more. Because I can still make the GNS construction, and I will get for phi a GNS NSF weight. I will introduce on n phi the following scalar product, A, B, phi, it's equal to phi of B star A. Look here. Phi is defined on B star A. Well, this is a scalar product, and we make the, you don't lose anything because the weight is faithful, so you have not to separate first. You just complete the space, and the space completed with this will be called H phi. And then you will still have the same kind of P sub phi defined on M on B of H phi, a star isomorphism. Well, let me put it so. Pi phi of M included in B of H phi, which is, this one is a star isomorphism. But here we have something more. Here we have how is given back the function f. How is given back from the NSF construction, the GNS construction for a weight, how the weight is given back. Here, the answer was the bicyclic vector gave immediately back the functional. Well, so that what should replace the vector psi? Well, let me say so. I hope Masamichi will not mind. Is a whole mess which replaces the vector psi phi. And that whole mess has the name of a left Hilbert algebra. Namely, let me denote by A sub phi this thing, n phi intersection n phi star. And look at the structure you get here. Here you get the following structures. Let me have. First, A is a part of M, so it has a multiplication. So on A sub phi, I have a structure of an algebra, and even the structure of a star algebra, because n phi star, it's in both of them. So that A phi has a star algebra structure. Let me put it is A sub phi. No, it's the multiplication, okay. Is a star algebra on one side. On the other side, it has a Hilbert, pre-Hilbert structure. So that means it is included in H sub phi, because n phi is included in H sub phi, right? So that on this algebra, we have a star algebra structure and the structure of a pre-Hilbert space. Okay, what we ask about this? The first thing is that we don't ask, we see that it is true. The first thing is that the map from A phi taking B, let me put B sub phi in order to say that this is looked in the Hilbert space. B sub phi is going to A sub phi times B sub phi, which means AB sub phi, which is also in A phi. This map is continuous. Why it is continuous, this map? I mean, in the Hilbert space norm, which is on A phi, simply because this thing can be written as P sub phi of A times B phi. And then the continuity is the continuity of the operator obtained in the GNS construction. Okay, the second thing is obvious, is... Sorry?
You assume the faithful now.
I assume that it is an NSF weight, so that it is faithful, of course. Okay, the second thing is that the following A sub phi, B sub phi times C sub phi is equal, phi is the scalar product also, it's equal to B sub phi times A sub phi star. Well, let's put A sub phi. This is A star phi, just in order to be more fancy in some sense. Okay, A phi star C phi. Well, this is absolutely obvious because these are values of phi in C star times AB or in A star C star star B, and these are equal. Right? X phi, Y phi, it's phi of Y star X. So that you have immediately this. So this is not a problem. Okay. Another thing is the following, the third thing. The third thing, at which hour should I stop? I have 1/4 of an hour only?
Yeah.
Okay. And third thing is that A phi square is dense in A phi. And this is because of the following computation. We take in the face of the weight F phi, which is M phi plus. We take an increasing net ui converging to 1. This exists because of the fact that the phi, the weight, is semi-finite. Okay, and then for an x in n phi, we have the following: x phi minus p phi of ui, x phi, phi. Up to now, it is only trivialities. And now we have majorization, namely it's less than twice phi x star x minus phi of x star ui x. You can see the x star ui x, x star y x, and x star ui x. There are the two guys here. And then you have phi of x star x and phi of x star ui, but these are less than 1. So that this is less than, okay. No, it's exactly, I can put ui instead of the wi. Okay, and this converges to 0. Converges to 0 because this converges to the identity. Okay. Now, this means that p phi of ui converges to identity. But because I have x there in n sub phi and ui is in m plus sub phi, this means that ui x belongs to n phi star. It's positive, so that it is n phi star. This is n phi star n phi. Okay? N phi star n phi. So that this belongs to m phi. This was the definition of m phi, which is at the same time the linear span of the face. Okay, we see that that means that m sub phi is densely embedded in H. And now A sub phi, which is n phi intersection with n phi star, which is included in n phi star n phi, because n phi is an ideal, and this is equal to m sub phi. No, I'm sorry. This is m sub phi is n phi star n phi is included. This is m sub phi. I have this inclusion because n phi is a left ideal. being a left ideal, n phi star n phi is in n phi, and the same way is in n phi star. As this is densely embedded in H, it follows that also A phi is densely embedded in H, so that A phi is densely embedded in A. Now, I can repeat this argument again with an UI and A phi. And then I will get that A phi square is dense in H phi, so is dense in A phi. You see that this replaces, again, the Xi phi. Because in Xi phi, you have the 1. And 1 times x is x. And finally, there is a fourth property. The fourth property is that the map going from A phi, taking an A sub phi, going in A sub phi, I repeat, this means A star sub phi. In A phi, this map is closable conjugate linear densely defined operator. It is closable. Well, the proof of this thing is not difficult, but it is again near the main idea. Namely, let's look first at the case of a normal positive form. In that case, A sub phi is equal to m psi naught. Psi naught being the phi is equal the vector state of my psi naught. This contains x psi naught goes to x star psi naught belongs to A is m psi naught A phi. And why to consider only this operator? Because we have the algebra and its commutant. And then you have, on the other hand, the algebra I will, without any reason for the moment, denote by A prime phi, equal m prime psi naught, contains x prime psi naught, goes to x prime star psi naught in m prime psi naught. I will name this operator is S0, and this operator I will put the name F0. And now what happens? I make S of x psi 0 times x prime psi 0. Okay. This is equal to x star psi 0 times x prime psi 0. It's equal to. I put this one in here and this one in there because they commute. So that this is x prime star psi 0 times x psi 0. So that means F0 of x prime psi 0, sorry?
Why that A psi equals to M psi 0?
I don't understand.
A psi equals to M psi 0.
Oh,
A
S of x psi 0 is times x prime psi 0 is x star psi 0 times x prime psi 0 is the same. It's equal to now. This means x prime star x star psi 0. One is in the commutant, the other in the algebra. It means x star x prime star. And I take this one and I put in the other side, and it remains x prime star. Is that okay? Good. Times x psi 0. Now, if we look at this equality says that the operator S naught is included in the adjoint of the operator F naught. It may be strange for you to see the candidate for the adjoint in the same part, but this is because of the conjugate linear operators. So that what you see here is that S naught is included in an adjoint operator. Every adjoint operator is a closed operator. This is included in a closed operator. It is closable. So that this is, say, the main thing in the case of a linear functional. Now, what happens is that in the general case of a weight, you have that the weight phi is the supremum of an increasing family of normal positive. This is enough to prove that also the operator which is put here, this operator, I will call it S naught, this operator is closed. Now, having that definition of the normality, it is easy to show that the operator is closable. The details are written. You can have the papers. And in principle is the following thing. What means to show that an operator is pre-closed or closable? If a sequence xn converges to 0 and t of xn converges to something, the something should be also 0. That means the closability of the operator. Now, this is expressed in terms of phi, but in terms of phi means that it happens the same thing almost for every linear functional here. For the linear functional, you have the conclusion, and you put these things together. It's just a tedious writing on the blackboard, this thing. But it is remarkable because in the original Tomita-Takesaki theorem, it was the case to assume that normality means this thing, while normality meant usually some other thing, namely that for sequences of positive elements, increasing sequence of positive elements. By the way, if you ask instead of this, the weight to be countably additive is not equivalent to the normality. Hagerup gave an example on this. So this is for today, and tomorrow I will begin the theory, the construction of the J and of the theory in the case of a bicyclic vector. The proof in this case has all the ingredients of the general case, but it's simpler, and it gives to you an idea. Because, you see, here, in that case, I'm sorry for 1 minute more. In that case, you have on one side m psi naught, on the other side you have m prime psi naught. Here you have only this, only the algebra with the 1, 2, 3, the 4 properties. This notion is called a left Hilbert algebra. So what you have just a left Hilbert algebra. You have to construct an associate right Hilbert algebra, A prime, and then to go back to associate a left Hilbert algebra to this one in order to get something which can be used as M psi 0 in here. These things are, of course, very important for the general theory, but for filling the proof of the Tomita-Takesaki theorem, I think we can restrict to the bicyclic vector, the existence of a bicyclic vector. The proof I will use is the proof, a very smart proof, given by Van Delle in 72 or something like that. Let me say that the most natural proof of the Tomita-Takesaki theorem is the one which is in the book of Masamichi. That's natural. It's tedious, it's difficult, it's long, but it's natural. Another more or less natural proof has been given by Hagerup, but he never published it because the paper of Van Delle appeared. In the paper of Hagerup, it's, to prove that delta power n, m, delta power minus n is the same thing as m, is rather easy for integral things, at least at a formal point of view. And then what used Hagerup was a theorem, a famous theorem of Clarkson. The theorem of Clarkson saying that an entire function which vanishes in the integral points and has a certain growth, then it is identically zero. That proof was also almost natural, but the most natural proof is that long proof in the book of Takesaki. Thank you.
Where can one find this Woofer's proof?
Sorry?
Where can one find this proof of Woofer's?
I don't have it. I used to have almost all the papers, but I don't have it. Sorry?
Proof is there in your book.
No. You mean, I mean not the proof of normality. What he asked, no. What he asked was, where can we find the proof of Hagerup for the Tomita-Takesaki theorem? That it is a preprint of Hagerup, who never published it. So I didn't see it. I just know what it's about. I thank you very much. Sorry?
My volume 2 of
Sorry?
Springer-Fellner.
Sorry?
It's in my second volume,
Yeah?
in the yellow.
Yes, I understand the spring.
Springer-Fellner.
You put the proof of Hagerup?
Yeah.
Ah, fine.
Yeah.
Fine.
But for students, that just to prove that the phi equal to supremum of the
But it's not about...
function bounded by phi, it takes about 20 pages. But when it comes to the actual application, your proof is normal because phi is that form. and so I made the footnote that those who want to go further to the
Masamichi,
high speed is not.
I also included in modular theory, I included the proof of Hagerup for normality.
Yeah.
But the question of Sunder was about the proof of Hagerup concerning your theorem with Tomita.
Yeah.
So that's a different thing.
You mean that the bounded operator approach?
Bounded operator approach was by Van Delle and Riffel. But what I mean is a very nice proof of Hagerup, which was never published, and I even don't have a preprint of it.
Well, but that was because the
Van Delle, of course, yeah, because Van Delle found it before. It is a.
I think that nevertheless he get the recognition because of that was shown when he was a student. And so that's enough for him.
So that I propose it to you to speak in the afternoon on the spatial theorem of von Neumann. On the other hand, the proof of the fact that that operator is closable, in the last detail, it's found in the notes which I distribute, and that's okay. It's not worth to go to the blackboard with such things.
Maybe I want to make a comment also. You wrote a P,
Yeah.
A sub P, but it is psychologically very nice to, instead of a P, P to the square root, P to the one half, and the view that as a not vector inside Hilbert space, but an infinitely long vector, and you cut down by operator, in operator algebra becomes the L2 element. And then that way, use intuitively, or to make any kind of a conjecture, for instance, what you want to prove, then it's very handy to have the P to the
Square root, okay. It's just
literature, but in my mind, I always
okay.
write.
Well, you see, I said it, and perhaps Masamichi would pardon me, that the singular B-cyclic vector was replaced by a whole mess. And the mess is a left Hilbert algebra. Thank you very much again.